Well, here's a fun but kind of crazy problem from Munker's book, 17.21. This problem was originally solved by Kuratowski in 1922, not all that long ago in mathematical terms. Consider the collection of all subsets A of the topological space X. The operations of closure and complementation, meaning taking the complement, are functions from this collection to itself. Show that starting with a given set A, one can form no more than 14 distinct sets by applying these two operations successively. So, well, the first observation is we only need to consider what happens when we alternate these two operations, right? Because if you have a set and you take the complement twice, you just get back the set that you started with. So that's not particularly interesting. And if you have a set and you take the closure twice, you, well, after taking the closure the first time, you already had a closed set, so another closure is not going to change anything. Okay? So if we introduce a couple new notations to make this all a little easier to write, I'm going to use L to represent the closure of A, and M to represent the complement of A. Didn't want to use C since they both start with the same letter, so I picked this, the second consonant in the word. Okay, so if we define L and M in that way, then all we need to consider are the sets that we get by sort of applying L and then M and then L, or M and L and M, and so on, where we alternate between the two operations. All right. Well, there's still infinitely many possible sets in each of those sequences there, so we need to find some repetition somehow. Well, here's one fact we can use, which actually is you're going to prove in one of your exercises in this section. For any subset B, the set X, the closure of the complement is the complement of the interior. Okay? If you draw a picture of this, it's pretty believable. But I'll leave that to you since it's a homework problem. So that's what we have. And then if you just take the complement of both sides, you get the complement of the closure of the complement equals, well, the complement of the complement, which is just the original set interior of B. Okay? Or in terms of our M and L notation, this is, well, first you take a complement, and then a closure, and then a complement of your set B. And that's equal to the interior of B. All right. One other fact that we're going to need, which has to do with interiors, is that if you have an open subset of X, not just any subset, but an open one, then that subset B is contained in the interior of the closure. Okay, we showed in a previous problem that we can't always put an equal sign right here. Turns out you can't always put a inclusion sign either, a subset sign. Okay, but you can if B is open, and here's why. The interior of closure B is the union of all open sets contained in closure of B. Okay? And in this case, B is an open set contained in closure of B. All right, so it's certainly contained in the union of all such sets. All right. So we get this inclusion, and then this one always holds, right? The interior of a set is contained in the original set. All right, well, if we just take the closure of everything here, then the inclusions will be preserved. So we get closure of B contained in closure, interior closure of B, contained in closure of B. Right, but closure of B is already closed, so the second closure doesn't change anything, and that's just closure of B. All right, and so you see that the beginning and the end of this chain of inclusions are actually the same thing. And that means that everything here has to be equal. Okay? And so actually, this is a typo, I meant to put an equal sign right there. All right, well, writing this in terms of our L and M notation, we have a closure of B on the left, on the right we have a closure, and then an interior, which we up here decided was complement, closure, complement, and then another closure. Okay. So we do have sort of some repetition in these sequences, but only if we begin with an open set B, right? Now the good news is we can generate an open set from these M's and L's, okay? Because if you take a closure of any set S, you get a closed set, and then you take the complement of that closed set, you get an open set, okay? So for any subset S of X, ML of S is always going to be open. So we can substitute it in our equation up here for B to arrive at this equation. And, okay, well that would hold in particular for A. But in general, what can we say? Any set of the form, one of these two forms that we looked at above with alternating L's and M's, with this pattern in it, 4 L's and 3 M's, as you see on the right side here, is equal to another set obtained by with fewer operations, right? You can basically throw away an LM from the end of this process, okay? So what that means is when you build up these sequences by adding more and more L's and M's on the left side, you might as well stop once this pattern appears, okay? So as you're building them up, if you start with an L, then you keep going and you get 7 sets, and then one more would give you this L, which would be the same thing as, well, this set right here, the 4th one, which we already had. So we don't, and the next one would be the same as the 5th one, and so on. So we don't need any more. And if you started with M, then, well, again, you get sort of 7 sets, and then one more would give you this pattern, and you could throw away 4 of them and get thrown back here. So altogether, there are at most 7 plus 7 equals 14 distinct sets that can be generated by applying these two operations to a given subset A of X. Now, we haven't proven that these are all different, right? And I mean, maybe only 5 of them are different. Well, that is the subject matter of part B. Find a subset A of, for example, the real numbers in the standard topology for which the maximum of 14 is obtained. And I stole this example from this website here. Basically, you take A, which is an open interval minus a single point, together with a closed interval, intersection the rational numbers, together with an isolated point. And for some reason, when you do sort of these 14 things to it, every single one of them is different. So it is possible to get 14 distinct sets from applying these two operations repeatedly. Okay? Although I suspect that most sets you might write down that aren't too complicated would probably start repeating before you get all the way through these 14. So there you have it. Kuratowski's problem is solved.